Okay, welcome to the last video in our series of renal lesson 1, basically the introductory lesson. This last video will give a very brief overview of some of the things that go into urine formation, some of the processes that are involved. So we went over the glomerulus, the renal corpuscle where your filtration takes place. We learned about all the filtration barriers in the last video. Let's talk a little bit about how that filtration is regulated, and it is largely through the contractile status of these arterioles, the afferent arteriole where blood enters and the efferent arteriole where blood leaves. So you guys will recall that vasoconstriction will increase the resistance to blood flow, and this is like kinking a hose. When you kink the hose, the pressure upstream of the kink goes up, the pressure downstream of the kink goes down. So we have this process of filtration taking place through our renal corpuscle here, and that is largely going to take place based upon how much pressure builds up in these capillaries. So if I want to decrease glomerular filtration, one thing I can do, and what your body will do, is constrict this afferent arteriole where blood enters this glomerulus. If I constrict here, the pressure goes down, and in fact all the blood flow goes down into this renal corpuscle, and so that means that you'll get less plasma flow and you'll get less filtration of plasma. So your GFR will drop if you constrict the afferent arteriole. If I kink this hose, the pressure upstream goes up, the pressure downstream goes down. Less pressure here means less filtration of water across this capillary wall into the renal tubule, okay? On the other hand, if I constrict the efferent arteriole where blood ordinarily exits, now I'm kinking the hose, pressure upstream goes up, and now I build pressure in these glomerular capillaries, and that means I've got more filtration of water taking place into this renal tubule, and I increase my glomerular filtration rate, okay? So one way that your body regulates GFR is through the differential contractile status of these two. When it wants to decrease GFR, it will often constrict this, and when it wants to increase GFR, it can constrict this. And if they both constrict, then it depends on which one constricts more, what effect you get, okay? So that's largely how filtration is regulated. So let's talk a little bit about how that blood flow is regulated. This is part of a process known as autoregulation. It is a way that the glomerulus regulates itself to keep glomerular filtration rate relatively constant. Now, extrinsic factors like sympathetic innervation will override this, but in the absence of that, this is the way that the kidney sort of automatically, or it's one way that the kidney sort of automatically responds to keep GFR more or less constant. And it does that by altering the blood flow to the kidney, that is the contractile state of the afferent and efferent arterioles. So let's take a look at this. It's a process known as tubuloglomerular feedback, and it is mediated by the juxtaglomerular apparatus, or JGA. This apparatus is highlighted here in the blue circle. So what you'll notice is that here's our glomerular capillaries, our Bowman's capsule, our proximal tubule, our loop of Henle, and then when we come to the distal tubule, it comes in very close to where this glomerulus is, and in fact the afferent and efferent arterioles sort of surround it, or it's the tubule is in a fork between the two arterioles. So these two are very close to this distal convoluted tubule, and if we take a closer look at this, in the distal tubule we have an area that is known as the macula densa, and that is what is primarily responsible for mediating this response. We also have granular cells here. They're not involved in the JGA response, the tubuloglomerular feedback. They're actually responsible for secreting renin, which we'll talk about at a later date. But nevertheless, this is the juxtaglomerular apparatus, as you see it here. So the way that this works, let's say that you have an increase in blood pressure, as you see right there, okay? And what this does is it increases the pressure in the glomerulus, okay? So it increases the hydrostatic pressure, and what that does is it provides a greater driving force for filtration of fluid into the Bowman's capsule and into the tubules of the kidney. So what you get is an increase in the glomerular filtration rate, okay? So the way the apparatus responds is you get this increase in GFR, you get an increase in tubule fluid flow through the through the proximal convoluted tubule, through the loop of Henle, through the distal convoluted tubule. You have an increased flow right here. And what happens is the macula densa senses that increased flow in this distal convoluted tubule. Okay, the mechanism's unknown. It's thought to have something to do with an increased delivery of sodium and chloride, but it's a little bit hazy right now and it hasn't really been worked out very well. But nevertheless, this macula densa senses that increased flow, and the macula densa, what it will do in response to that is it will secrete vasoconstrictors. It's thought that it might be ATP or adenosine or something related to that, but bottom line is the substance is unknown. But nevertheless, it's secreted locally and it diffuses. And what it does is it hits the afferent arteriole primarily, mostly, and it causes contraction of the arterioles. And so you would get an increase in resistance to flow and again, increased resistance here. It's like kinking a hose. Pressure upstream goes up, pressure downstream goes down. By constricting this afferent arteriole, you decrease the pressure in the glomerulus, the hydrostatic pressure, and therefore you decrease GFR. Okay, and so the GFR is decreased back toward normal. So this is autoregulation, where the kidney's trying to keep the GFR more or less constant. Now, do recognize that things like sympathetic innervation of these arterioles will override this. And do also recognize that all autonomic innervation to the kidney is sympathetic. So you know that all the innervation to arteriovascular smooth muscle is sympathetic, with a few exceptions. And the kidney in general is the same way. You know, innervation of pretty much everything that's going to be regulated by the autonomic nervous system. It's sympathetic only, no parasympathetic innervation. Okay? Okay. So let's talk a little bit about the process by which urine is formed beyond that. So we start with filtration, just like I said, and that is step one in the process of forming urine. And then we enter our renal tubules, and that is where tubular secretion, that is the addition of substances from the body, from the interstitium, or back into the renal tubule, because you want to excrete even more of that substance as much as you, often as much as you can. Certainly you want to excrete more than you've just gotten through filtration. And then there is also a process of reabsorption that takes place where substances are removed from the tubular fluid and added back into the body, into the bloodstream. Those are usually substances your body wants to keep because they're important to keep for the body. All right, so and again, these three things, in summary, you ended up determining how much of whatever substance you're looking at is excreted. All right, so let's take a closer look at that. First of all, we have the process of filtration here on the left, and that is where the substance is filtered across the barrier that we talked about in the renal corpuscle, from the glomerulus into Bowman's capsule and into the tubule. And this is the amount of substance that gets filtered. And generally speaking, if it passes freely through the barrier, you're going to end up with the same concentration here that you had in the plasma here. Okay? And so filtration is the first step involved in urinary formation. And if you have no reabsorption and no secretion, then the amount filtered is going to be the amount that's in your urine, okay? Now, we also have, with many substances in the body, the process of reabsorption going on. So here's filtration, we have these triangles here, and then reabsorption is the process by which these substances are removed and put back into the bloodstream. So these triangles have been added. So this represents substance that was removed through filtration, okay? They just make it a nice little empty space here. This is the amount they call the amount cleared. We'll talk about that in more detail in a later lesson. You can see these extra triangles are being added back. That's the process of reabsorption. And so we have 6 here that were filtered, we have 3 reabsorbed, and we have only 3 that are excreted in the urine. So when you determine how much of this is going to be in the urine, you take the amount filtered and you subtract the amount reabsorbed, and that leaves you with the amount excreted. On the other hand, if you have a substance that is secreted, that means it's filtered, and then extra substance is moved into the renal tubule, because you want to actually urinate more than you filtered, okay? And so this is a transport process where the substance is moved, extra substance is moved from the plasma into the renal tubule, so you end up excreting more here than you filtered. So you add the amount secreted to determine how much is excreted. So if you want to know all in all, if you have one substance that is filtered, reabsorbed, and secreted, then the amount excreted is going to be the amount filtered, minus the amount removed, the amount reabsorbed, plus the amount added back in to the renal tubule from the plasma. And this will give you the amount excreted. Okay? Good. That's all I've got. Thank you for your attention. I'll see you guys in class.